Welcome to Cambridge Chemistry channel with Sarwat Ahmed. In this video I will be solving 507042 May June 2023 paper. Let's start. Question number 1, a student investigates the rusting of iron. You know that condition of rusting of iron. Figure 1.1 shows the apparatus the student uses. So the conditions are moist air or air, and you can write down oxygen and water. So in experiment A, water is there, iron nail and apparatus. This is apparatus X, in which iron nail is placed in the water and air is provided. And in the experiment B, iron nail, dry air. So there is no water in the experiment B. So in the experiment C, oil is the barrier of rusting. You know, when you place oil over here, so air cannot penetrate in the water with this nail. So experiment C, it means most probably that rusting take place in I experiment A. No rusting because no water is there, and also no rusting because there is a barrier between iron and air. Experiment C, no rusting is there. Name apparatus X. Test tube is the apparatus. State why stopper is used in experiment B. So water vapor does not enter in the tube. So prevent the water vapor to enter in the prevent the water vapor to enter in the experiment B. State why the water in experiment C is boiled before use. Oxygen is removed. State why a layer of oil is used. Oil act as a barrier to prevent oxygen to enter in the test tube. So the experiment are left for 1 week. Predict in which of the experiment the nail will have rusted. Experiment A, because both air and water, the condition of rusting is provided to experiment A. So there is water absent in the experiment B, and here air absent in the experiment C. So that's why rusting cannot take place in experiment B and experiment C. Question number 2, aqueous ammonia is a solution of ammonia gas. Student titrates 2 samples of aqueous ammonia A and B with 0.500 mole per dm cube hydrochloric acid. The student does 4 titrations, 2 with A and 2 with B. The student step 1 rinses and fills the burette with 0.5 mole per dm cube hydrochloric acid. Step 2 uses a volumetric, and please keep it in mind that don't use distilled water to rinse the burette. Always rinse the burette with the liquid which is carried out in the experiment. Step 2 uses a volumetric pipette to add 25 centimeter cube of A to a conical flask. Add 5 drops of methyl orange indicator to the conical flask. Place the conical flask on a white tile. Why white tile is used? To observe the endpoint clearly, or to observe the color change clearly. Step 5, add 0.500 mole per dm cube hydrochloric acid from the burette while swirling the contents of the flask. adding drop by drop near the end point until the solution just changes the color. Empties the Step 6, empties the conical flask and rinses it with distilled water. Always rinse the conical flask with distilled water. Step 7, repeat step 2 to 6 and repeat steps 2 to 7. Use aqueous ammonia B instead of aqueous ammonia A. There are two samples which we are using in this experiment, sample A and sample B. Both are ammonia. Figure 2.1 shows the burette reading for the two titrations with A. So this is 15.2 is the final burette reading and 0.0 is the initial burette reading. The volume used is 15.2. We get this volume by subtracting initial from final. Similarly, 30.2 of second titration is the final burette reading and 15.2 initial burette reading for experiment 2. 15.2 and by subtracting 15.2 from a final burette reading we get 15.0. So B part is figure 2.2 shows the burette readings for one of the titration with B. So this is initial, this is final. Record the burette readings for titration 4 in table 2.2. Complete table 2.2 with the volume used in each titration. 34.9 is the final burette reading and 0.2 is the initial burette reading. So this is 34.7. So this is titration 4 which is given over here. So this is 0.6, this is 0.6, this is 5 and this is 6 till here, this is 6 and by subtracting 0.6 from 35.5 we get 34.9. Explain why the student uses a white tile in these titrations so that change can be visible. Calculate the mean volume of 0.500 mole per dm cube of hydrochloric acid needed to neutralize 25 centimeter cube of A and B. So by using 15.2 plus 15.0 divided by 2, so we get 15.1 and mean value volume of acid needed for solution B is 34. By adding these two volume plus 34.9 divided by 2 we get 34.8. The equation for the reaction between hydrochloric acid and aqueous ammonia shown HCl plus NH3 to form NH4Cl. Use the mean volume of acid needed to neutralize 25 centimeter cube of A in D to calculate the concentration of ammonia A. So we have 0.500 is the concentration of HCl and 15.1 in volume of ammonia. Volume of for solution A, mean volume for solution A is 15.1. So this is volume of acid HCl. So by using this formula, concentration into volume in centimeter cube divided by 1000. So we know that we have 0.500 is the concentration and concentration always in mole per dm cube. This is in mole per dm cube. By calculating this value we have 7.55 into 10 raised by 2 minus 3. So this is the mole of HCl. So we have 1:1 ratio, 1:1 ratio between HCl and ammonia. So if the moles of HCl is 7.55 into 10 raised by 2 minus 3, so this is we get mole of ammonia. This is ratio of HCl and this is ammonia. So mole of ammonia is 7.55 into 10 raised by 2 minus 3. Now concentration, we know the concentration formula is mole over volume into 1000. because volume in centimeter cube always, so multiplied by 1000 to equalize the unit, because concentration is always in mole per dm cube. This is mole over volume into 1000. So we know the volume of so this is not 28, this is 25, volume is 25 centimeter cube. So by dividing, by calculating this, this is mole, this is volume in 25 centimeter cube of A, we get concentration is 0.302 mole per dm cube. This is concentration of ammonia. Now calculate the volume of ammonia gas measured at room temperature and pressure at RTP dissolved in 25 centimeter cube of A. The volume of 1 mole of any gas at RTP is 24 decimeter cube. So we know the volume of ammonia gas, that is 0. This is mole of the ammonia gas. So mole is equal to volume of gas divided by molar gas volume, which is equal to 24 decimeter cube. So volume of gas, we have mole, and we can calculate the volume of gas by using mole into 24. So this is 7.55 is the mole of into 10 raised by 2 minus 3 is the mole of ammonia, into 24 is equal to 0.1812. So this is the volume of ammonia gas. Now use your answer to D and F. This is F and this is D. This is the volume of B. Use your answer to D and F to calculate the volume of ammonia gas measured at RTP dissolved in 25 centimeter cube of B. We know that the mole of HCl in 1000 centimeter cube we have, because we have 0.500 is the concentration of HCl. So it means in 1000 centimeter cube mole is 0.500. So if 1000 centimeter cube has 0.500 mole, then what would be the mole in 34.8 centimeter cube used in experiment B? So the mole would be 0.0174. We need to take mole ratio between ammonia and HCl. So there is 1:1 ratio between in this equation. So 1:1 we get mole of ammonia by using mole ratio. So now using mole ratio volume, 1 mole has, we know that 1 mole has 24 decimeter cube volume. So what would be the mole, what would be the volume in 0.0174 mole? So by using cross multiplying, we get the mole of ammonia is 0.42 decimeter cube. Use always two significant figure. Answer should be two significant figure for volume, because over here 25.0, so the two significant figure, answer always given in two significant figure. The student rinses the burette with 0.500 mole per dm cube hydrochloric acid immediately before it is filled. Explain why the student should not rinse the burette with distilled water immediately before it is filled with 0.500 mole per dm cube hydrochloric acid. You know, I have earlier told you that burette always washed with distilled water. As some water left in the not with distilled water, always rinsed with the volume which is used in the burette afterwards. So if we wash burette with distilled water, what happened? As some water left in the burette which makes acid dilute. So this is the reason why we don't wash the burette with the distilled water. Suggest why universal indicator is not suitable for use in this titration. Color change could not be visible. So that's why universal indicator cannot be used in these titrations. Methyl orange can be used. Question number 3, student investigates solution W and X, W and solid X. W is green in color, contains iron 2 ions. Describe how W can be shown to iron 2 plus ions. So this is sodium hydroxide. We can check by using sodium hydroxide aqueous or ammonia solution. So add sodium hydroxide till the change can seen, and then excess green precipitate which are insoluble in excess. Excess W is added to acidified potassium manganate solution. So when potassium manganate is added in the green solution, so it is going to oxidize Fe2 plus to Fe3 plus. So it is oxidized. Fe2 is the green colored solution and Fe3 is yellow. So when we add potassium manganate in this solution, you know, manganate ion is purple in color, and when it is manganate oxidized iron 2 to form iron 3, then its color will become yellow because iron 3 salts are yellow in color. So describe the color change seen from purple to yellow. Describe the observations made when a few drops of aqueous ammonia and then an excess of aqueous ammonia are added to the mixture from 2. A few drops red brown precipitates because iron 3 is present. Now iron 3 is present in this solution. So red brown precipitates which remain insoluble in excess of sodium hydroxide. Excess ammonia. This is excess ammonia, few drops ammonia. Solid X is a shiny gray metal. The test the students does on X are shown in table 3.1. Some of the observations for these tests are also shown. Test on solid X. Add excess dilute acids to X in a test tube. The gas produced is tested. Dilute acid in solid X, and X is a solid. If gas is produced, then it means that solid disappears, so solution remains colorless and becomes warmer. Add dilute nitric acid then aqueous silver nitrate to some of the solution from test 1. So solution remains colorless. It means if solution remains with addition of nitric acid and aqueous silver nitrate. So these are the test of halide ions. This is the test of halide ions, and halide ions containing maybe Ag plus chloride ions, bromide ions or iodide ions can be present if we proceed this test. So solution remains colorless, it means halide ions are absent. Add dilute nitric acid, then add aqueous barium nitrate. So you can confirm this from the test given at the back of the paper. You know, this is these three are halide ions: chloride, bromide, iodide. With acidified dilute nitric acid, then adds aqueous silver nitrate. If chloride ions are present, white precipitate. If bromide ions are present, cream precipitate, and if uh, iodide ions are present, yellow precipitate observation. So there is no color change in this part, so that's why halide ions are absent. So that's why halide ion solution remains colorless. So halide ions are absent in this solution. Add dilute nitric acid, then add aqueous barium nitrate to some of the solution from the test 1. White precipitate, it means sulfate ions are present. You can confirm from the test given at the back of the paper. You know that the sulfate ion acidified with, this is sulfate ion test, acidify with dilute nitric acid, then add aqueous barium nitrate. This is observation white precipitate. So it means sulfate ions are present in this solution. Sulfate ions are present. Now, part 1, predict the identity of the gas produced in test 1. Describe how the student tests the gas to confirm its identity. Hydrogen gas, and you know that this is a redox reaction, and when gas is given off, that reaction is exothermic. So always colorless solution become warmer. The gas produced is tested, remains colorless and becomes warmer. It means this is exothermic and hydrogen gas is evolved. Hydrogen gas bring lighted supplant in the gas jar. Gas produces pops in flame. The observation for test 1 for incomplete. Number 2, observation for test 1 are incomplete because over here solid disappears, solution remains colorless. So one observation, that is the effervescence of gas, because gas produced is here, so effervescence of gas should be there in the observation. So effervescence of gas. State the conclusion you can make from test 2. No halide ions are present because solution remain colorless. No precipitates are formed. State the conclusion you can make from test 2. No halide ions are present. State the conclusion you can make from the test 3, that is sulfate ions are present because with addition of barium nitrate, white precipitates are formed. Identify the acid used in test 1, that is sulfuric acid. Suggest the identity of the metal X, zinc or magnesium can be. This is shining gray metal. A solid X is a shining gray metal. So it means with addition of acid, hydrogen gas is produced and solid disappears. And you know that moderate reactive only react with the with dilute acid, so it can be zinc or magnesium. Baking, question number 4. Question number 4, baking soda is used to make bread rise. When baking soda is heated, decomposes and carbon dioxide gas is released. Baking soda also decomposes gradually when it is stored. The longer the baking soda is stored and less the carbon dioxide it releases when it is heated. This is the same experiment which I have discussed in the variant 4.1. Plan an investigation to show which of two different samples of baking soda has been stored for longer. Your plan should include the use of common laboratory operators and the two samples of baking soda. No other chemicals should be used. Your plan should include operators needed, the method to use, the measurement to take, the variables to control, how to use the results to determine which sample has been stored for longer time. You may draw a diagram to help you answer the question. Number 1, electronic balance, Bunsen burner, test tubes, gas range and thermometer. And you know that there are that there are two types of variable, dependents and independent. And this what do you mean by dependent? What we measure, and independent, what we change. And you know method, measure the same mass, these are the controlled variable, same mass of baking soda for both the sample. Heat the sample Bunsen by using Bunsen burner by keeping temperature constant. Measure the volume of gas, carbon dioxide collected in the gas range. Controlled variables, heat both the samples to the same temperature. This is the controlled variable, same temperature, same amount intensity of flame and same amount of same surface area of baking powder. This is again another controlled variable, same sample, same mass, same temperature and same surface area of baking soda is used in both the samples. Conclusion: sample which produce more carbon dioxide gas is stored for shorter time. So this is the result which we obtained from this experiment. Hopefully you understand this paper. If you understand this video, please press the like button.